This is going to be a series of notes on the integrated rate laws. Best way to view these notes if you just received the presentation itself is to put this into presenter view. So in case you needed to use, let's say, a periodic table or a calculator that's on your computer, you can switch in and out of the presentation without it stopping. So here we go. We're going to be looking at three different sets of graphs. One of those sets is for the 0th order. The second set we're going to look at is for the first order reactions. And the third set of graphs is going to be for the second order reactions. The game we're going to be playing when we look at these graphs is we need to look for the straight line. That's it. And every single time we see a straight line, we can make a new equation. And that new equation is going to follow the same pattern that you did in algebra, which is y is equal to mx plus b. So here's a 0th order reaction. The rate of the reaction is equal to k times a to the 0th power, which at this point you should know that when something is raised to the 0th power, this goes to 1 and it just drops out. So that said, the game we're playing is look for the straight line. Can you find the straight line? Hopefully you figured out it's the first graph. The first graph is a straight line. You'll notice, though, that it does have a negative slope. That's because the concentration is decreasing over time. That means, by the way, the slope is going to be equal to the rate constant for the 0th order reaction, but it's going to be the negative slope is going to be equal to it. Or for that matter, if you're looking down here, slope is equal to minus k, which literally means if the College Board or any other test or quiz gives you any other graphs for, let's say, natural log of concentration versus time or 1 over the concentration versus time, you can just ignore them flat out. Don't even have to pay attention to them at all. The only thing you will need is the concentration versus time graph if the concentration versus time is a straight line. So you'll notice that, again, we can still ignore these. You'll notice that in the bottom left corner of your screen, you'll see that it says a concentration of A at time 0 is equal to the negative K times T plus concentration of A at time 0. So you'll notice that that follows the Y is equal to mx plus b format. So what are we going to use? We're going to use this exact equation of concentration of A at time t is equal to minus k times t plus concentration of A at time 0. Annoyingly, the College Board puts a slightly different equation on there. What do they do for their equation sheet? They move the b value or the intercept onto the same side as the y. So you'll notice that it says the concentration of A at time t minus the concentration of A at time 0 is equal to minus k times t. These are both the same equations, but all the problems that I'm going to use are going to be the ones from the College Board equation sheet, so that way you're accustomed to it. So here is an example problem for the 0th order reaction. There are 4 parts, part A through D. I'm going to pause here for a moment for about 10 seconds so you can go to your screen, hit pause, and then you can actually try these problems because the remainder of these slides will actually go through what the answers are on how to do those problems. So I'm going to give you a moment to do that. All right, folks, so hopefully you had a chance to pause and then you tried those problems. After you tried the problems, hopefully you started this video again, and now we should be able to take a look at the answers. For A, since it's a 0th order reaction, the equation you're going to use is rate is equal to K times the concentration of B raised to the 0th power. Since the concentration of B raised to the 0th power is going to be 1, the rate constant will be equal to directly the 2.5 times 10 to the negative third molarity per second, which means the units for that rate constant is molarity per second. When you're looking at the next problem, what we're doing is substituting in all of the values that we've got. And you'll notice that with that, once you substitute in the concentration of A at time 0, and you're substituting in the minus k times t, you should be able to plug in those variables and then solve algebraically. Same deal with the next problem. The next problem, you'll notice that we've got the concentrations are now plugged in, and I have K plugged in. We're solving for T over here in yellow, and you have 193.6 seconds. Part C, same deal, except this time we're solving for the initial concentration, which is A at time 0. Plug in those numbers, and you should be able to get 0.245 molarity. With any luck, I didn't have any typos in my calculations, and those answers are accurate. If they are not accurate, please let me know, and I will double check my work. All right, game number 2. This is a first order reaction. Here are 3 graphs. All of these graphs are from the same experiment. The experiment itself that was measured is this first one here of concentration versus time, but then we ended up applying some mathematics to those concentrations to be able to get the natural log versus time graph as well as the inverse of concentration versus time graph, or 1 over concentration of A. Can you spot the straight line? So with any luck, you'll notice that the section that is here in the middle is the straight line. I was figuring you probably figured that out pretty quick, but you might be wondering why I have the green portion circled. The green circle can be turned into the red circle by applying calculus. When a first order reaction equation of concentration versus time is integrated, yay, calculus, it can yield a straight line graph of the natural log. You do not need to know calculus for the AP exam. You just need to be able to spot the straight line and to recognize that the y-axis is the natural log of A. So, can you make an equation of y is equal to mx plus b based off of this line? With any luck, you were able to say, well, the natural log of A at time t, which would be our y, is equal to the negative k, because once again, the slope is going downward, so the k is the negative value of the slope, plus the natural log of the initial concentration, which would be the y-intercept. And just like before, the College Board does put this in a little bit of a funky order. They do move this natural log of concentration of A at time 0 to the other side of the equation with their y value. So once again, like with the 0th order, I'm going to use this style of equation instead, just to make sure that we're being consistent with the College Board and what equations you're going to see. So here is another first set of example problems, but this time using the first order reactions. So use these values. Again, I'm going to pause for about 10 seconds or so you can pause, try these on your own, and then you can check the answers afterwards. I'll pause here for about 10 seconds. Welcome back. So now we're going to take a look at the answers for these problems. Just like before, in order to be able to figure out the value for the k, we can plug in the standard rate law or the differentiated rate law, where the rate is equal to k times q to the first power. Plugging in the values of the rate that was given times the concentration that was given raised to the first power, so we just have to leave it the way it is. Then algebraically, when we solve it, we get a value for k for the rate constant of 4.0 times 10 to the negative second per second. Or the other way I can say this is 0.04 per seconds. For part B, I know that a bunch of people probably are not 100% perfectly comfortable with natural log. Why did I give so much information on this page? Is because I wanted to make sure that you saw what I did for every single step, and I'm going to talk through these. So here we go. The first order reaction. The equation for it is the natural log of the concentration of A at time t minus the initial concentration, the natural log of the initial concentration, being equal to the negative k times time. So with the first problem, you'll notice that we're trying to solve for the concentration of time, or concentration of Q at time of 37 seconds. You'll notice I plugged in the 0.250 molarity in for the natural log of the initial concentration, being equal to the negative constant, which is the same constant that we had from part A, or 0.04 per second, times a 37 seconds. So then from each one of these, I showed what I changed from line to line by highlighting it in yellow. The 37 seconds times the negative 0.040 seconds becomes negative 1.48. For the next step, I took the natural log of 0.250 molarity. And if you have a graphing calculator or a TI variety graphing calculator, in the bottom corner here, I showed a picture of the button that you would need. This is the natural log. This natural log button is what you would hit. You type in natural, you would hit the natural log button, and then 0.250, and you would get minus 1.386. And that's what changed from the third row down to the fourth row. Then you'll notice that because I have the negative in there from the answer and I'm subtracting it, those two combine together to become a positive. But then to get this number to the other side, I have to subtract them. So then what I would have would be the natural log of the concentration of Q at time will be equal to negative 2.866. Then how do you get rid of this natural log? So we cannot, the way that a natural log is removed is natural log is a function like multiplication or division. You cannot divide by natural log to get rid of it. You have to have the anti-function for the natural log. The anti-function for natural log is raising things to the power of e. So again, looking back at the calculator in the bottom corner over here, you'll notice that the natural log button is here. And then the second function version up here is e raised to the x power. So in order for me to get this into the final answer, I'm going to take e and raise it to negative 2.866. When you take e, raising it to the natural log, the e and the natural log will cancel each other, and what I would get is just going to be the concentration of Q. So the concentration of Q is equal to 0.569 molarity. For solving for problem C, all we need to do is plug in the values. This time it's again natural log of 0.16, minus the natural log of 0.500, and then the values are given. This one is a little bit easier since you don't have to worry about trying to get rid of the log function. Time for this one would be 86.05 seconds. As far as significant figures, technically it should be 86 seconds for the answer. For the last part D of the first order reactions, again, we're still using that same integrated rate law with the natural logs in them. You'll notice I plugged in the values just like I did in the first problem, except this time it's the initial concentration that we're trying to solve for. So when we take the log, or the natural log of 2.56 times 10 to the negative third molarity, you get an answer of negative 5.933 minus the natural log of the initial concentration. When we have the negative K value times the time, we get negative 3.88. Then if you combine those terms, you would have 2.053, because remember when you move this this negative 5.933 to the other side, this negative becomes a positive. You then have the negative natural log is equal to the 2.0 times 2.053. That becomes a negative number. To get rid of the natural logs, you raise things to the power of e, and you would have an answer of 0.1283 molarity. We will do more practice problems like this one when we get back to class, of course, but this is a good sample problem to start from. Last game. Here we go. Can you find the straight line? This is for a second order reaction. So you'll notice the concentration versus time graph, not linear, not linear. Natural log for a second order reaction is not linear. And the last of inverse of that is a linear value. But this time you'll notice that the slope is actually a positive slope, so we don't have to worry about negative values with it. So as I'm sure you figured out once again that the value for the slope is a positive number. And again, we can turn this concentration versus time graph into this 1 over graph Again, you can do it mathematically, but basically the calculus version of doing that would make it work, or that's the equation that can make that happen. The middle graph for a second order reaction is completely worthless at this point. It is not needed. The natural log of concentration versus time for a second order reaction is not going to be helpful. Again, you don't need to know calculus to be able to be successful. All you need to be able to do is find the equation or find the straight line and know what equation to use for it. So now that we know that the straight line graph is a straight line graph at 1 over concentration of A, we're going to use that 1 over concentration of A to figure out an equation for the line. Give you a moment to try to see what you think that would be. All right, so continuing. It would be the inverse of concentration of A at time t is equal to K times time plus the inverse of the initial concentration. So you'll notice that we have these inverse functions. And just like with the previous equations, the College Board does move the B value over with the Y value of Y is equal to mx plus B. So you'll notice that we have the K being the slope and the T being our X on the right side. And here we go. We've got another equation, but this one is going to be again for second order reactions. We'll again use that equation that the College Board uses for the sample problems that are next. Here is the sample problem for the second order reaction, and I will give you about 10 seconds once again to pause, as well as to try the problems, and then when you play it again, I will come back and go through some of those answers with you. All right, folks, here we go. Second order rate equations. Again, rate law is equal to K, rate law constant times concentration of A raised to the second power. And you'll notice that the other equation is now going to be this integrated rate law that we're going to have available to us to work. For the first portion, when we're trying to solve for K, we can solve for K by plugging in the rate that was given is equal to K times the concentration squared. So that means K is equal to 0.0694 molarity to the negative first and seconds to the negative first. Notice that the units have been changing every single time from different orders of reactions. So you do need to be careful with those units. Here are the answers to C, D, and E, and B, C, and D, excuse me. And you'll notice that I have the rate law equations sitting out. Each one of these rate law equations is the integrated rate law. If we're looking at B, you'll notice that here is the variables. The variable that we were missing in the first equation was the concentration of the H3O plus ion at 45 seconds, which would be this spot here. Once you do the algebra to solve for it, you should end up with an answer of 0.191 molarity. The most common wrong answer that I get from people is 5.228 because they did not inverse their answer to be able to get to it. What they solved for when you get this would be 1 over the concentration. So that means you have to inverse that to be able to get the answer that you need for to be correct. The second part, or part C, I should say, is again, we're solving this time for time. Again, plug in the numbers, solve for T. T should be 150.0 seconds. I think the answer in my calculator was something like 149.97. And again, technically for this, a total of 3 sig figs should have been fine. But 150, or if you even did 149 seconds, that would have been fine as well. And then the last problem, once again, plugging in the values, you have the concentration, the initial concentration of the H3O plus ion as the blank that we're trying to solve for. And the answer that you should have received is 0.3236 molarity. Once again, if any of mine seem to be off from your answers because I might have had some type of typo, please let me know, or it might be something that we need to go over to make sure you've been calculating it correctly. All right, so if you were to actually look at the College Board equation sheet, what's on the College Board equation sheet? There are 4 equations underneath kinetics, and they are listed right there. Nice, big, and bold so you can see it, hopefully, and they are in order. zeroth order, first order, second order. So literally when you look at the equation sheet, hopefully you should be able to memorize that they are in numeric order, but it starts with 0. It does not start with 1. So then you might be looking at this and saying, okay, what's that fourth equation doing at that in the bottom corner there? Well, that is a half-life equation, but that half-life equation is only for first order kinetics. So it is only in a half-life equation that will work in a first order reaction. And we're going to do a couple of sample problems with those as well. Do you have to worry about a half-life equation for 0th order or second order? You do not. One of the things that I want to point out, though, while we're looking at this, we got 0th order, first order, second order. In the 0th order, you'll notice that the half-life in the 0th order depends on the concentration of the reactant. Same thing with the second order reaction. The half-life is determined in part by the concentration of the initial concentration that you have. That is not true for first order. First order half-life is 100% consistent. It always takes the same amount of time to get rid of half of the amount of stuff that you have left. So what do I mean by half the amount of stuff that you have left? Well, if you're starting at a 1 molarity at the very top up here, it takes, according to this amount of time to get to 0.5. So that means it's cut its concentration in half. From 1 down to 0.5 took a certain amount of time. It will take the exact same amount of time for that 50% to get to 25%. And then it's going to take the same amount of time for that 25% to get to 12.5%, or again, cutting it in half. So if I'm at 1 to get to 0.5 is 1 half-life. To get from 0.5 to a quarter, or 0.25, would be 1 half-life, and so on, and so on, and so on. So it consistently steps down for the half-life at a consistent amount of time. So the amount of time needed for the remaining concentration to cut in half is a good definition for half-life. All right, so here are some first order, for half-life problems with the first order equation. All you need to use on this, you don't need the integrated rate law, you don't need the differentiated rate law. The only thing that you need is that half-life equation of where T of 1/2 is equal to 0.693 divided by K. Plug it in and solve. Again, I'm going to pause here for about 10 seconds so you folks can work on it. All right, so from here, oh, actually, I did make a mistake in my statement before. Oh, actually, no, I did fine. You can actually solve all of these without having to use any other integrated rate laws. You could just use the half-life problem to do so. Here are the answers for them. We will go over these in class if you do have questions. Once again, here's the key summary of half-life. Only thing to worry about half-life is for first order. The first order half-life is consistent and does not have concentration in the equation. You can use this in the concentration versus time graph to be able to determine that the reaction is a first order. If you're seeing it's taking the same amount of time to cut in half every time, you can tell that that's going to be a first order reaction. So for a first order reaction, the differentiated rate law is rate is equal to K times A to the first power, or you can leave the 1 out. The integrated rate law, which is also listed by the College Board on the side over here, is given. And then the half-life equation has a K in it as well. Those Ks for the first order reaction are all the same value for K. They are interchangeable with each other. So a review of all orders of reaction. Gonna give you a moment to try and fill out this entire chart. What is the differentiated rate law for each of these? The integrated rate law? What units do you have for K? If you were to have a sketch of the straight line graph, which one of these would have the Y value, or what would the Y value be for the graph for each of those? And which one of these have a consistent half-life? I'll wait about 10 seconds so you can hit pause and take a moment to copy those down and fill that out. So here are the answers. Here are the rate laws. Rate laws, the differentiated rate law, granted, it says you need to memorize them, but chances are you've been able to do this so far where rate is equal to K times the concentration of something raised to some power. And if it's zero, it's not there because it becomes 1 when you raise anything to the power of 0. The first order rate law has the concentration of A raised to 1, and the second order is the second. Great. As far as the integrated rate laws that are there, you do not have to memorize those. You just have to use the equation sheet. Now, if you want to memorize the units for K, you're welcome to. You'll notice that basically starting with 1m up on top, it constantly removes a molarity every single time. But the other thing you can do is actually just show your work with units for a change, and you'd be able to actually get the values that you need and the units that you need. What is on the y-axis in order to be a straight line graph? For the 0th order reaction, it's just the concentration. For the first order, it's the natural log of the concentration of A. And for the second order, it's 1 over, or the inverse of the concentration of A. And the only one out of those that has a consistent half-life is the first order. All right, so now there's some graphic problems, so graph problems with these. The graphs that I gave you were in order every single time. They were always consistently the concentration first, the natural log second, and then the inverse graph last. But that's not necessarily the way that you're going to get them when it comes time for a quiz or an exam, or for that matter, the AP test. So what you have to do is look at the graph, look what's on the x-axis or on the y-axis, and then figure out which equations that you're going to use, and you'll be able to then figure out also the order of the reaction. So here's some practice time. This one you don't need to pause for, I hope. Take 10 seconds, figure out what order of the reaction this one's going to be. This is a second order rate law because this is 1 over the concentration over time. And that's where you got the straight line. These other two, while this graph over here of concentration versus time might be useful, the natural log value graph is actually not useful at all. But now that we have this, what we can do is ignore those other two and answer a few questions. You should be able to use the graph to solve all 5 of these problems, or at least you'd be able to use them to figure them out. Take a moment and do that. Again, you might need to hit pause. I will pause so you can get to the keyboard. All right, the answers. First order, well, I'm sorry, excuse me, second order. Why is it a second order? It's a second order because it is a 1 over, or an inverse function of concentration versus time. How do you figure out the value of K? It's the slope of this line. And since it's positive, we don't have to worry about that plus minus stuff. So what values did I use? I used the 0, 10 and 100, 20 to determine the slope. What is the concentration at 100 seconds? All it is I took this value at 100 seconds, and it gives me an answer of 20. But that means that I've got 1 over the concentration is equal to 20, and then the inverse of that would be 0.05 molarity. The concentration at time 0, same thing. All I have to do is pull the number off the graph. It's 10. But what I need to do is take the inverse of that, and that's going to give me my 0.1 molarity. And then calculate the concentration at 200 seconds. How did I get this 1 over 30 stuff? Well, what I did is I noticed that it went from 10 up to 20 in 100 seconds. And since it's a straight line, it's going to keep being a straight line, which means it's going to increase in the next 100 seconds, going up to 200 seconds. It's going to increase by another 10, which means it's going to go up to 30. So I was able to just extrapolate by looking at the graph and estimating what it's going to be beyond to be able to solve for the 1 over 30. And the 1 over 30 would be 0.0333 molarity. Here's another set of graphs. What is the order of this reaction? With any luck, you saw that there was the natural log function is the straight line graph, which means it's a first order reaction. So here are 5 values. Once again, you should be able to use the graph for the majority of this, but this time the dots don't line up so pretty. They don't line up exactly on the dots as pretty as they did before. I think the prettiest one might be this one over here, but I'll let you figure out which one you want to use. Take a few moments to pause the video and answer those questions. All right, folks, the answers are coming up quickly here. You ready to go? Here we come. It is a first order reaction because it is a straight line graph on the natural log of concentration versus time. The value of K, again, I figured out a slope. I started at 0, 0, just because that would make my life a lot easier. And then I noticed that I could also use the 15 is kind of on a good junction point. So I said that it was at 5.2 for the graph, and I used that to calculate my slope. So the concentration at time 0. At time 0, it's 0. So the natural log of x is equal to 0. What is the value then for x? Well, I have to raise e to the 0th power, and when I raise e to the 0th power, I get an answer of 0.1 molarity. For the excuse me, it should be 1 molarity, not 0.1 molarity. My mistake. When we take the concentration at 10 seconds, I would take that, well, let's see, 10 seconds. We look at the graph. It's about negative 3.55, perhaps. Some people might have had their number a little bit different, so your answer might be a little bit different than mine, but the value that I chose was this, and that's what I have for my answer. And then calculating the concentration at 20 seconds, same deal. I took the value at 20 seconds, looked to be about -7, which was just about halfway between -8 and -6, and then solved for it. All right, folks. So that pretty much wraps it up. We are definitely going to be doing more problems like this in class the next time we see each other. If you have questions, please let me know. Thank you for watching the video, and hopefully this has been helpful.